Science Fantastic with Professor Michio Kaku. I'm a professor of theoretical physics at the City College and also the City University of New York. And today we're going to talk about nothing less than the entire universe. We've had programs about health, about medicine, about robotics, artificial intelligence. We've had programs about the moon, about the solar system and stars. But now we're going to talk about the whole shebang, the universe itself. Our special guest today is astronomer Paul Sutter, author of an exciting new book called Your Place in the Universe. We should also point out that he's a professor in the Department of Astronomy at Ohio State University, and he has his own blog, Ask a Spaceman! And so we're going to talk to him today about, well, where are we anyway in this great universe of ours? Well, once again today, we're going to talk about where are we? I mean, that sounds like a stupid question, right? But think about it for a moment. Where really are we? We're on the Earth. We're going around the sun. The sun goes around a galaxy, the Milky Way galaxy. The galaxy probably goes around the Virgo supercluster. And where does that go? I mean, where are we anyway in this universe? So with us today is astronomer Paul M. Sutter, author of the book, Your Place in the Universe. So, Paul, glad you could be on Science Fantastic.
Oh, thank you so much for having me.
Okay, first question for you is, how did you as a youth, as a young kid, first get interested in science?
I remember growing up as a kid, I was devouring books of all kinds, including astronomy books, but also books about dinosaurs, books about life, books about engineering. I remember being a voracious reader, but I really didn't get into astronomy really until my late teens and early 20s. And when I was in college, I was a computer science major and plugging along, not having the greatest time. And I took an astronomy elective because I always had this background interest in astronomy. And a switch flipped. And within a week, I switched majors to physics, and I never looked back.
And when did you get your first telescope? Because a lot of astronomers say that it was the first telescope that sent them on this great cosmic journey. But, well, what happened to you?
I did have a telescope. I had a small refracting telescope growing up. Got it probably in my early teens. Mostly it collected dust in the corner of my room.
Is that right?
It was something I had that I enjoyed occasionally, but my spark didn't really ignite until I was much older.
Yeah, in fact, I tell young people that instead of buying thousands of dollars of the top-of-the-line telescope, first buy some binoculars. You can get some great images of the moon. And, of course, you're not going to see much when you look at the stars because the stars are so far away. But if a young kid comes up to you and says, what kind of telescope should I buy for an amateur who's beyond the stage of getting a telescope, binoculars, what would you advise them?
A few companies make some really nice 8 to 12-inch Schmidt-Cassegrain telescopes that are very portable, extremely easy to use, and get you beyond things like the Galilean moons or the phases of Venus, get you some great images of nebula, of double stars, of planetary nebula, even galaxies like the Andromeda Galaxy. And that's always my next recommendation because it's not too crazy expensive, and for the money, you can pack a lot of punch.
Okay, well, let's just jump right in your book, Your Place in the Universe, Understanding Our Big, Messy Existence. First question, well, where are we then? Tell us where we are with respect to the solar system, the galaxy, and even beyond that. Where are we in the universe anyway?
Right, so we are members of the Milky Way galaxy. We're on a small branch of one of the spiral arms, about two-thirds of the way out from the galactic core. Our own Milky Way galaxy is a member of a few galaxies, a group called, appropriately enough, the Local Group, which is us, Andromeda Triangulum, and a bunch of smaller ones. All together as a group, we are merging together, and will do so in about 5-ish billion years. And also all of us as a group are falling towards a cluster of galaxies called the Virgo cluster, which is home to about 1,000 galaxies. Us and Virgo and a few other clusters as a larger group are also falling into a much larger cluster. We're a member of a supercluster called Laniakea. And this supercluster of galaxies is just one branch, one chunk, one section of a much vaster, grander structure that we call the cosmic web. And the cosmic web literally fills up the universe. It is made of galaxies, and it's exactly what it sounds like. There are long, thin ropes of galaxies, dense knots, which are the clusters, and there are vast, empty voids, which almost nothing in them.
Okay, now let's try to get a sense, first of all, of distances in our universe. If you shine a flashlight to the moon, in about 1 second, the light will reach the moon. But now we're talking about stars. So if I shine a flashlight at the stars, how long will it take, first of all, to reach the nearest star, then the nearby stars, and then the more distant stars, but stars you can still see at night?
Right. The nearest star is Proxima Centauri, which is 4.5 light years, around 4 light years away, which means it'll take your beam of light from your flashlight about 4 years to get there. And the stars, the typical stars you see in the night sky are anywhere from tens to hundreds, in some cases 1,000 or so light years away. So we're talking 10 years, 100 years, 1,000 years. The most distant thing you can see with the naked eye is not an individual star, but it is the Andromeda galaxy itself. You can see it's a fuzzy patch about the size of your outstretched fist. And that's the accumulated light of around 1 trillion stars in the Andromeda galaxy. And that thing is 4.5 million light years away. So the light we're getting from the Andromeda galaxy right now is very, very ancient indeed. And then when we're talking about the universe, when we're talking about cosmology, the study of the universe, it's those scales at the millions of light years. That's the beginning step for cosmology, of really entering this realm.
Okay, Paul, we're going to have to take a short commercial break, but afterwards we're going to continue a discussion of, well, where are we anyway in the universe? Stay tuned. Welcome back to Science Fantastic with Professor Michio Kaku. Today we're going to try to answer that question, that cosmic question, where are we anyway? The book is called Your Place in the Universe, Understanding Our Big Messy Existence by Paul M. Sutter, an astronomer at Ohio State University. And he's the author of a great book that hopefully will try to make you understand, first of all, how big the universe is and where we are with respect to the universe. Now, the ancients, when they looked at the night sky, asked themselves a simple question. How many stars are there in the universe? If there are an infinite number of stars, which of course is the logical statement to make, if there are an infinite number of stars, then everywhere you look, you should see a star. In which case, the entire night sky should be white and not black. And in fact, your eyeballs should melt. Your eyeballs should get an infinite amount of light from an infinite number of stars, because everywhere you look, there are an infinite number of stars. This is called Olber's paradox. It's a very old paradox going back hundreds of years, and it was finally solved, believe it or not, by the poet Edgar Allan Poe, the mystery writer. He was an amateur astronomer, believe it or not, and before he died, he actually wrote down the answer to this paradox. So tell us a little bit about Olber's paradox, and why such a simple statement. Why is the night sky black rather than white? Why does it have philosophical, theological, and cosmological implications?
Yeah, there's this sense that the night sky is fixed. It is called the firmament, after all, and it's just always been there, that the universe simply is, and while us and our lives here on Earth are always messy and changing and chaotic, the stars are still the stars, and they just existed. And you can easily extend this concept to the whole entire universe, that the universe simply exists. It is infinitely large and has been around forever. It is just infinite in all dimensions. But once you make this very simple statement, you run into a problem, which you mentioned, Olber's paradox, which is an infinitely old, infinitely big universe has an infinite number of stars, and the light from those stars has had an infinite amount of time to reach us, which means the sky should be ablaze. So the universe can't be both infinitely old and infinitely big. At least one of those things has to give. And it wasn't until the early 20th century that we had the evidence that our universe is definitely not infinitely old. It might be infinitely big, that's still an open question, but our universe has a finite age, which is itself a remarkable, groundbreaking statement that our whole entire universe, everything that we claim to exist, has an age. And that age is around 13.8 billion years. And just that fact is very unsettling and kind of difficult to wrap your head around, and yet there is the evidence.
Now, Edgar Allan Poe, the mystery writer, before he died, stated that there has to be a cutoff. That is, since an infinite amount of stars that are infinitely old would give you an infinite amount of light hitting your eyeball, and therefore the sky should be white and your eyeball should melt, he said that if you go back far enough, it stops. There has to be a cutoff. In other words, there has to be a genesis. There has to be a beginning to the universe. Now, I think about this when I take a shower at night. You know, you have nothing to do taking a shower at night, but then you realize, well, the night sky is black. But that means there was a creation. There was a point where the universe had a beginning. And that is basically an existential realization that the night sky is the greatest predictor of something that we call, well, now we call it the Big Bang. What are your thoughts?
Yeah, that's exactly it. The universe has a finite age. And then when Edwin Hubble in the 1920s discovered that galaxies on average are receding away from us, and in fact receding away from each other, there's a few conclusions you can make, but the one that survived all other experimental tests is that we live in an expanding universe. Our universe gets bigger and bigger every day, which means in the past it was smaller and smaller, and in the distant past there were no stars, there were no galaxies. Our universe was crammed into a very, very small volume. And this is the fundamental framework of the Big Bang Theory, which is our modern picture of cosmology and of the universe, and how we arrive at the conclusion that our universe does have a finite age. And so there has not been infinite time for light from distant stars to reach us. And so the night sky will be mostly black.
Now, people ask the question, what is the object that is the farthest that the Hubble Space Telescope can see? Well, the Hubble Space Telescope can see very distant stars until finally you get to the Big Bang itself, because the universe, the night sky is a time machine. You're looking into the past. Now, when we look at the Big Bang itself, it's basically kind of disappointing, but it's in the microwave region. So tell us a little bit about the microwave background radiation that is, in some sense, the afterglow of the creation of the universe.
Right. So this was the discovery of this background radiation was a major linchpin for Big Bang cosmology and our modern understanding. And it comes from the realization that a long time ago, our universe was a lot smaller, a lot hotter, and a lot denser. And when it was about a 1/1,000,000th of its present volume, it was so hot and so dense, it was a plasma. It was in a different state of matter. And then as the universe expanded and cooled, it switched from being a hot, dense plasma to a neutral gas. And when that switch happened, it was like a light went off, or a light switch flipped, and a bunch of radiation was released. This radiation This occurred when our universe was about 380,000 years old. This radiation soaked the universe and at the time was literally white hot at a temperature of a few thousand Kelvin. Then as the universe expanded and cooled, this radiation stretched out and cooled off all the way down into the microwave band. And in fact, it completely covers our sky. There's this leftover light from this moment in the early history of our universe that completely covers our sky. It was predicted to exist by a team of researchers at Harvard back in the 1950s, and they're beginning to put together the pieces to build a microwave antenna to detect this, when unbeknownst to them, down the street, a couple of engineers at Bell Labs had built a microwave detector and accidentally discovered it. Eventually, after a year or two, they got together and they realized what they had found, which is this background light. It's an image of our universe. It's a baby picture of our universe from when it was only 380,000 years old, which is like having a picture of you when you were only 7 seconds old.
Now, when you look at this picture, and you can go to nasa.gov and actually see the photograph in the microwave range of this ancient radiation, you see tiny little ripples. Now, these ripples, of course, expanded because the universe expanded after the Big Bang. And didn't these ripples eventually become the cosmic clusters of galaxies and supergalaxies?
Yes, exactly. So if you look at a picture of the cosmic microwave background, the latest image is from the Planck satellite, which was joint between NASA and the European Space Agency. You'll see some big splotches, and these splotches are tiny little differences in temperature, tiny little differences in density, like 1 part in a million different. But you'll see some big splotches, which are actually created by sound waves crashing around in the early universe. That's pretty cool. But you also see lots of tiny little bumps and wiggles. And those tiny little bumps and wiggles are the seeds of later structure. So earlier I was talking about how we're a part of this vast cosmic web, and there are clusters and filaments and all that kind of stuff. That was all seeded very early on, and we can see a picture of it in the cosmic microwave background.
Well, we have to take a short commercial break, but after the break, we're going to talk about dark matter, dark energy, and the multiverse of universes. Stay tuned. Science Fantastic with Professor Michio Kaku. Once again, our special guest is astronomer Paul M. Sutter, author of a new book. It's called Your Place in the Universe, Understanding Our Big, Messy Existence. And he's an astronomer at Ohio State University, and he has a blog that you can get into, Ask a Spaceman, ! And he also has a website, pmsutter1word.com /outreach. Well, where we last left off, we were talking about the universe, but now let's talk about what is unknown about the universe and still causing lots of controversy. First of all, dark matter. What is dark matter? We thought we scientists pretty much knew what the universe is made of, but we were wrong. So every high school textbook is now being rewritten to take into account the fact that we are in some sense clueless as to what most of the universe is made of. This is embarrassing. So what are your thoughts?
I actually wouldn't call it embarrassing. I'd call it exciting. It's always great to have new mysteries out there in the universe because that's job security for people like me. And dark matter is one of these enduring mysteries. We first had hints of its existence way back in the 1930s. And then really in the 1970s with astronomer Vera Rubin, studying motions of stars within galaxies. And then ever since then, we've had this evidence piled and piled on that there's more to the universe than meets the eye. That when you look at all the hot glowing things, like stars and nebula and clouds of gas and dust and galaxies, it's just not most of the matter. That if you look at a galaxy, what you can see only represents, say, a quarter or 20% of the actual amount of stuff. That most matter in our universe simply doesn't interact with light. It doesn't glow. It doesn't reflect. It doesn't refract. Just doesn't talk to light at all. We can only learn of its existence through its gravitational effects, through the way that it can bind stars together inside of a galaxy, or bind galaxies together inside of a cluster, or bend light, or the very existence of the cosmic web itself is really a structure made of this so-called dark matter. And the visible matter, the matter we know and love, just kind of floats along for the ride.
Now, if dark matter did not exist, isn't it true that the Milky Way galaxy would have been basically unstable and blown apart? And that most of the universe of galaxies that we know it, would have become unstable?
Yes, this is a very surprising thing where life itself may owe its existence to dark matter, because in the very early universe, once you set up these seeds of structure where things are starting to pool together, things are starting to grow, the matter, the normal matter, is still really hot. It has a hard time binding itself together because of its high temperature. But the dark matter doesn't care. The dark matter starts pooling in by itself and eventually drags the normal matter along with it. But if you were to get rid of the dark matter, then you'd have to wait a lot longer for the normal matter to start building itself together. And at the present time, 13.8 billion years later, you simply don't form galaxies. You don't have multiple generations of stars. You may not have any stars at all because you can't get enough matter together in the same spot at the same time. And so it could very well be that the existence of our Milky Way galaxy and even life is due to the presence of dark matter throughout the universe.
Okay, well, let's take another short commercial break. Once again, you are listening to Science Fantastic with Professor Michio Kaku. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, our special guest today is Paul Sutter, astronomer at Ohio State University, author of a new book, Your Place in the Universe, Understanding Our Big, Messy Existence. And also, I should point out, go to my website, mkaku.org, and find out what I'm up to. Once again, it's mkaku.org. And I'll be on a book tour. The book is called The Future of Humanity, Humanity in Outer Space. What happens not a year from now, but what happens decades from now, centuries from now, when one day we may go to Mars and even beyond that. Find out in my book, The Future of Humanity. Well, Paul, when we last left off, we were talking about dark matter, a form of matter that we know holds the galaxy together but is invisible and is awfully hard to predict its properties. Now we have something called dark energy, which is even larger than dark matter in terms of its contribution to matter energy in the universe. So tell us a little bit about that, dark energy. And once again, if you want to win a Nobel Prize, figure out what dark matter is, and an even bigger mystery, dark energy. What is dark energy?
Yeah, this is crazy. So we've known for about 100 years, ever since Edwin Hubble, that we live in an expanding universe. It's bigger every day. But we discovered something surprising about 20 years ago. This expansion of the universe is accelerating. So not only is the universe getting bigger and bigger every day, it's getting bigger and bigger, faster and faster every single day. We have no idea what's going on, but we give a really cool name to it. We call this dark energy. It could be, well, we don't know. It could be a new form of gravity that we didn't understand before. It could be something to do with the vacuum of space-time. It could be an energy associated with the vacuum itself. It could be a new force of nature. We're kind of in the dark, hence the name dark energy. We're at the stage now where we're designing surveys and telescopes just to measure the effects of dark energy better. Like, is it changing? Was it worse in the past? Is it getting better now? Or is it going to get worse in the future? Just how strong is it today? We're trying to answer these very, very fundamental questions so that we have some sense of what to do next with our theories.
Now, the poets ask the question, will the world end in fire or ice? Well, we know partially the answer. The Earth will end in fire when the Earth is eaten up by the Sun about 5 billion years from now. The Sun itself will die in ice when it becomes basically a burnt-out dwarf star. And the galaxy will probably die in fire when it collides with Andromeda. And we have this galactic collision taking place. But now let's talk about the universe. Is the universe going to die in fire or ice? What are your thoughts?
As far as we can tell, if we take the current status of the universe with its makeup of normal matter and dark energy, and none of those things change, and we just run the clock forward, then our universe will die in ice, where eventually stars formation will shut off. In fact, star formation in our universe is already on the downhill slope. Eventually, hard to tell, about 100 trillion years from now, the last star will be born. And about 10 or 20 trillion years after that, the last star will die. There'll be no more stars in the universe, and there'll just be leftovers like black holes, neutron stars, white dwarfs, planets here and there. And eventually, over enough time, all those objects will dissolve, including black holes. And over incredible amounts of time, I'm talking like 10 to 100 years, all that's left in the universe is a thin soup of fundamental particles that are slowly cooling down and approaching absolute zero and getting more and more spread apart. We call this the heat death of the universe because it is the death of heat.
Now, Freeman Dyson, physicist at Princeton at the Institute for Advanced Study, has speculated that, well, maybe one day we'll have to leave the universe and go into the multiverse. So we'll talk about that after the break. Once again, you are listening to Science Fantastic with Professor Michio Kaku. And the question is purely hypothetical. Are there other universes out there? To Science Fantastic with Professor Michio Kaku. With us today is Paul M. Sutter, author of the book Your Place in the Universe, Understanding Our Big, Messy Existence, and he's a professor of astronomy at Ohio State University. Well, let me ask you a purely hypothetical question about whether or not there are other universes out there. When you take a look at the nature of the universe, it seems like it was fine-tuned to create human beings. For example, if the nuclear force were a little bit stronger, the sun would have burnt out billions of years ago and we wouldn't be here. If the nuclear force were weaker, the sun would never have ignited to begin with, and we still wouldn't be here. But the nuclear force is just right to create a warm sun and to create DNA and life. And if gravity were a little bit stronger, then our universe would have collapsed billions of years ago in a big crunch. If gravity were weaker, then the universe would have been blown apart and we would have hit the big freeze. So gravity is tuned just right to allow for a life. So some people think that either the universe really is fine-tuned to create intelligent life, that intelligent life is preferred, or there are parallel universes out there, dead universes, and we simply won the crapshoot. That there are universes where stars never ignited. There are universes where stars burnt out really quick, and we just happen to be in the one where life exists. So what are your thoughts now? Because we're now leaving cosmology and entering philosophy and theology, in fact. What are your thoughts?
Right. So this is such a thorny question, and you framed it very well, is here we are in the universe, we're existing, And what we see around us are certain fundamental constants. We see the speed of light, the strength of gravity, the four forces of nature, et cetera, et cetera. And obviously this set of physics supports life because, hello, here we are. And it seems a little weird. We don't really like coincidences in physics. And so we have to wonder, why is it this set of physics rather than another set of physics? It could be this is the only universe and there's various mechanisms that we have yet to understand that lead to this kind of physics, and then here we are. Or it could be that, say, exotic processes in the very early universe generated multiple kinds of universes with different kinds of physics, and some of them are very interesting and have life. Some of them are very, very boring. Some go nowhere right off the bat, but there's a whole panoply, a whole buffet of universes. And so the reason we happen to find ourselves in the one that supports life is because it's the only kind that will support life. Now, that is more of a philosophical argument than a physics argument, but physics is trying to tackle this multiverse question. The challenge is we have no direct evidence for a multiverse. We simply don't know. And the physical theories that lead to a potential multiverse are, I don't want to say sketchy. Sketchy is too strong of a word, but they're speculative. We don't have a lot of hooks physically into a multiverse. And so the current status of that question is, I don't know.
Okay, well, the leading theory that fits the data of the Big Bang is called inflation theory, where there was a turbocharged expansion much faster than originally thought. But since inflation is a quantum theory, it can happen again and again and again. And we had Alan Guth on our airwaves. He's the creator of the inflationary universe theory, professor at MIT, and he believes that universes are constantly being created, even as we speak right now. Big bangs are happening someplace in the cosmos. Universes are being created. So what are your thoughts, given the fact that even though inflation does fit the data for our Big Bang, is speculative as to whether or not there are other Big Bangs out there? But what are your thoughts?
Yeah, exactly. So we have a lot of evidence to suggest that something like inflation, this turbocharged expansion, happened in the very, very early universe. But we don't understand the actual mechanics, the actual physics of that event, of what drove it, how long it lasted, how it operated, how it wound down. And it might be the case that any theory of inflation, any model you cook up, automatically leads to something like a multiverse, but it may not be the case because, honestly, we don't fully understand the physics. This is something that we can't access with, say, particle colliders. We can only access it by studying the very early universe, and that's kind of challenging. So it could very well be that once we crack how inflation works, that this automatically leads to the conclusion that there is a multiverse, but maybe not.
Okay, now, of course, we are talking about speculation now, but if you take a look at the cosmic microwave background photograph, the photograph that shook up the world of cosmology, showing that the Big Bang did in fact happen, you see, well, what looks like some splotches. Now, there should not be any splotches there. It should be pretty much uniform, except these tiny little quantum ripples. There'll be some splotches in it. And some people think, even though this is pure speculation, that it's the remnant of perhaps another Big Bang, or the remnant of perhaps a collision with another parallel universe. Now, of course, this is still speculation, but what are your thoughts? Shouldn't the cosmic microwave background radiation should be totally smooth, right, except for these tiny ripples? But why do we have these splotches?
Right, the cosmic microwave background should be a good test of the multiverse. We have no firm evidence of a multiverse from the cosmic microwave background. There are some strange features in it for sure, but we can explain it with much more mundane reasons. it.
Okay. Well, Paul, unfortunately, we've run out of time. Once again, your book is called Your Place in the Universe, Understanding Our Big, Messy Existence. Your website is pmsutter.com, and your blog is Ask a Spaceman. So thank you so much for being on Science Fantastic.